Before galaxies, before planets, there were only clouds, vast oceans of hydrogen and helium suspended in darkness. From that silence, gravity began to pull. Pressure grew and what was once scattered began to gather. Cold gas condensed into dense pockets, the first seeds of creation. Inside these invisible chambers, matter collapsed further, forming the hot hearts of what would become stars. As compression continued, temperature rose, until hydrogen fused into helium, and the first light in the universe was born. Fusion marked the transition from chaos to structure, from silence to radiance. Every stellar nursery, from Orion to the Carina Nebula, is a laboratory where gravity sculpts energy into light. Columns of dust, jets of plasma, and newborn suns surrounded by swirling disks, all parts of the same ancient pattern. Stars are not born gently. Their creation is violent, a battle between gravity pulling inward and radiation pushing outward. But from this conflict comes balance. Each new star stabilizes, shining for millions or billions of years, transforming the raw elements of the universe into the building blocks of life. Even now, within every glowing cloud and every faint speck of starlight, the process continues. The birth of stars is not history, it is the ongoing heartbeat of the cosmos. When a newborn star ignites, it enters the longest and most balanced phase of its existence, the main sequence. Here, gravity and energy reach a perfect equilibrium. The inward pull of matter is exactly countered by the outward pressure of radiation from nuclear fusion within the core. At this stage, hydrogen, the simplest and most abundant element, becomes the fuel that sustains the cosmos. Inside the core, at temperatures exceeding 10 million Kelvin, hydrogen atoms collide and merge into helium, releasing immense energy as light and heat. For smaller stars, this process follows the proton-proton chain, a steady and efficient pathway. For larger, hotter stars, fusion proceeds through the CNO cycle where carbon, nitrogen, and oxygen act as catalysts. Every photon produced in this reaction travels outward, scattering and reflecting. Some take thousands of years to reach the surface and from there they journey across the galaxy. The light we see from the stars is ancient, each beam a record of ongoing equilibrium between destruction and creation. A star's lifespan is determined by its mass. Massive blue giants, burning with intensity, live fast and die young, exhausting their hydrogen in just a few million years. Smaller, cooler red dwarfs live almost forever, quietly glowing for trillions of years. Between them lies the golden balance, stars like the sun, whose stable warmth nurtures the conditions for life. This period is not dramatic, yet it is essential. It is the time when stars define themselves, when their structure and identity remain constant. For billions of years, they shine, unchanged in form but ever-changing within, transforming hydrogen into helium, light into memory. And in that slow fusion, the universe maintains its rhythm, the steady heartbeat of creation that fills the void with radiance. After millions or billions of years of quiet fusion, the balance that sustained a star begins to falter. The hydrogen in its core, the fuel of its radiance, is finally exhausted. Gravity, no longer countered by the same pressure from fusion, begins to pull inward once again. As the core contracts, its temperature rises dramatically. Hydrogen still remains in the outer layers, and as the heat increases, those layers ignite. Fusion moves outward into a hydrogen-burning shell, while the inner core, now composed mostly of helium, continues to shrink. The result is dramatic. The star's outer layers expand outward, cooling as they spread. What was once a stable main sequence star now swells into a vast, luminous red giant. Its radius may increase hundreds of times. The surface temperature drops to around 3000 to 4000 K, giving the star its deep orange or crimson hue. But the core, under immense pressure, becomes a forge once more. When its temperature reaches about 100 million Kelvin, helium fusion begins. Through the triple alpha process, 3 helium nuclei combine to form carbon and later, oxygen. The star's structure becomes layered, each shell fusing heavier and heavier elements. For low and medium mass stars, this cycle ends with carbon and oxygen. For the more massive ones, fusion continues beyond, creating neon, magnesium, silicon, sulfur, and finally iron. Iron marks the limit. No energy can be extracted from fusing it, and at that boundary the stellar journey nears its end. From afar the red giant phase is beautiful but deceptive. Its surface glows softly, yet beneath it rages an engine of transformation, forging the elements that will someday become planets, oceans, and life itself. Even in its aging, a star serves creation. Its death is preparation, the slow alchemy of the universe turning energy into substance, and substance into memory. Every massive star carries within itself the seeds of its own destruction. For millions of years, it has burned with brilliance, forging ever heavier elements in its core. But once it reaches iron, the process halts. Iron cannot yield energy through fusion, it consumes rather than gives. At that moment, the balance that held the star together, between gravity and radiation, finally collapses. The core implodes in a fraction of a second. Gravity crushes the matter inward until it becomes so dense that protons and electrons merge into neutrons. Temperatures spike to billions of degrees. The outer layers, no longer supported, fall inward, only to rebound violently off the rigid neutron core. The result is an explosion of unimaginable power, a supernova. For a few fleeting weeks, a single dying star can outshine an entire galaxy of hundreds of billions of suns. Its brilliance expands outward in a shell of gas and plasma, scattering the elements it created throughout the cosmos. There are several ways such cataclysms occur. In Type II supernovae, a massive star, at least 8 times the mass of the Sun, ends its life in core collapse, leaving behind either a neutron star or a black hole. In Type Ia supernovae, a white dwarf in a binary system steals material from its companion until it exceeds its critical mass and detonates in a thermonuclear explosion. Each explosion is more than destruction, it is creation renewed. The calcium in bones, the iron in blood, the gold in rings, all are remnants of such ancient deaths. Supernovae are the universe's way of recycling matter, ensuring that the atoms forged in one generation of stars become the building blocks of the next. Astronomers have witnessed these events across time and space. The Crab Nebula still glows with the remnant energy of a supernova recorded by ancient observers in 1054. SN 1987A in the Large Magellanic Cloud gave modern science its first close look at the process in action, the last heartbeat of a star frozen in light. When a star dies this way, it does not vanish. Its ashes drift across interstellar space, merging with clouds of gas, seeding new worlds. From its death, galaxies are enriched, planets are born, and life becomes possible. A supernova is not an ending. It is the sound of the cosmos taking a breath, destruction becoming memory, and memory becoming the raw material for new creation. When a star's light fades, what remains depends on its mass, on how much gravity it must fight to survive its own death. Not all endings are the same. Some stars fall gently into silence. Others collapse into the most extreme states nature can allow. For stars with less than about 1.4 times the mass of the Sun, the end is quiet. Their outer layers drift away as glowing nebulae, and the exposed core remains behind, a white dwarf. It is no longer burning fuel. It shines only with the leftover heat of its long life. A sphere of degenerate matter, where electrons press so tightly together that gravity can fall no further. Over billions of years, this ember cools, fading eventually into invisibility, a black dwarf, a ghost of a once living sun. 4 heavier stars, between 1.4 and 3 solar masses, gravity wins a greater victory. When the core collapses after a supernova, electrons and protons merge, forming neutrons. The result is a neutron star, only about 20 kilometers wide but denser than an atomic nucleus. A single teaspoon of its material would weigh billions of tons. Many of these remnants spin rapidly, emitting beams of radiation. Pulsars, cosmic lighthouses flashing through the dark. The Crab pulsar at the center of the Crab Nebula is one such relic, a reminder of both destruction and endurance. And for the most massive stars, greater than about 3 times the mass of the Sun, even neutron pressure cannot resist gravity's pull. The collapse continues, unstoppable, compressing all matter into a point of infinite density, a black hole. Here, space and time curve inward completely. Beyond its event horizon, no light, no signal, no information can escape. Cygnus X1, the first black hole ever confirmed, remains one of the most powerful examples, devouring matter from its companion star, releasing X-rays that betray its unseen hunger. Each of these remnants, white dwarf, neutron star, black hole, is a monument to gravity's patience. They are not failures of creation but its most precise expressions. In their silence, they hold the memory of the processes that once made them burn. They are the punctuation marks in the sentence of stellar evolution, reminding the cosmos that even death is structure, and even collapse is continuity. The death of stars is never an ending, it is a transformation, a return of substance to the great cycle of creation. When a massive star explodes as a supernova, its outer layers are hurled into the interstellar medium at incredible speeds. Those expanding shockwaves sweep through surrounding space, compressing nearby gas clouds and enriching them with new elements: carbon, oxygen, silicon, iron, gold. Each atom born in the stellar core is released into the cosmic sea, waiting to be gathered again. Over millions of years, these remnants mix with colder clouds of hydrogen and helium, forming vast molecular nebulae, the birthplaces of the next generation of stars. The dust and debris of the old become the raw material of the new. From one cycle to the next, the universe refines its chemistry, building complexity from simplicity. Every new star carries the legacy of those that came before it. Our own solar system is a direct descendant of such ancient processes. Roughly 4.6 billion years ago, a cloud enriched by previous supernovae collapsed under gravity, forming the Sun at its center. Around it, the remaining dust and heavy elements coalesced into planets, worlds of rock, metal, and ice. The gold in human jewelry, the calcium in bones, the oxygen in every breath, all were forged in the hearts of long-dead stars. In this sense, every living being is both ancient and renewed. The atoms that make up every cell once drifted through nebulae, burned within suns, and were scattered by explosions that outshone galaxies. Matter does not vanish, it changes form, moving through endless cycles of creation and decay. The cosmos is a great recycler. Nothing is wasted, nothing is truly lost. Each death plants the seeds of new beginnings. Each supernova writes the ingredients for life into the fabric of space. And from that quiet continuity, the story of the universe continues, generation after generation, light after light. There is no true death in the cosmos, only transformation. The universe is a great cycle, a rhythm of light turning into matter and matter returning to light. Every ending becomes a beginning, and every beginning carries the memory of what came before. A cloud condenses into a star. The star burns, shining for millions or billions of years. When its fuel is gone, it collapses and explodes, scattering its essence into the dark. That debris drifts through space, cools, and joins with other clouds, forming once again a new star, a new system, a new chance for life. It is an eternal circle. Nebula starts, supernova, nebula again. No star lives in vain. Each one leaves behind more than light. It leaves elements, structure, potential. Hydrogen and helium gave birth to carbon and oxygen. Those elements formed planets, oceans, and living beings that now look back at the sky and wonder where they came from. Every atom and every breath, every cell, every heartbeat once burned inside a star's core. Calcium, iron, gold, nitrogen, all were created in stellar furnaces, spread through supernova winds and gathered again into new forms. The universe builds, destroys, and rebuilds, endlessly. The light that once illuminated the first star still moves through space, touching worlds that did not exist when it began its journey. In that light lies the continuity of existence, the proof that creation never ceases, that energy never fades, it only changes form. We are that transformation made conscious. We are the echo of ancient fire, the living continuation of stellar memory. And when our own light fades, we too will return, our atoms drifting back into the dark, waiting to shine again. Every atom of life was once the heart of a star.